speaker of today is Surya. Boy, that speaker. Surya from Spotify. He's a senior machine learning engineer, and he's going to talk to us about reinforcement learning for music recommendations. And I love that he picked a machine learning term. His term that really represents him is logistic regression. So he can really only make yes-no decisions. Just kidding. Ba-dum-bum. Thank you, Surya.
Thank you. Hey, would it be possible to get the speaker notes on the slide? It's fine. Okay, I'll start. Yeah, good afternoon, everyone, and thanks for sticking around for what is probably the last presentation for the day. I know many of you are tired. So, my name is Surya Kanoria. I'm a machine learning engineer at Spotify, primarily working on content personalization. Today, I'm here to discuss about our experiments with reinforcement learning for music recommendation. More specifically, playlist generation, because music recommendation is such a broad term. Just a disclosure, this is not my work alone. Like, there is a massive team of talented colleagues who have been working along with me on this. So it's not like just my project. Right, so automatic playlist generation, why is it even important? When the user opens the Spotify app and they go to a playlist, we want to provide to them a unique, personalized sequence of tracks which caters to their listening preferences. And we want to provide them with a very satisfying, unique experience. At the same time, we recognize that several of our users listen to music in the background. For example, I primarily listen to music when I'm running or cooking dinner or engaged in other such activities. So this is a laid-back listening experience as opposed to a foreground listening experience where the user is actively engaged in the application. And if they don't find things according to their taste, they can just switch things around. So while each user consumes music in their own way, we want to provide them with a coherent listening experience to maintain the flow or the vibe of the music. And for these reasons, it is important. Automatic playlist generation is a very relevant and practical problem for us to provide the users with unique, programmed, and personalized content. We discussed why automatic playlist generation is important, but where does reinforcement learning come into play here? For this, you have to understand that music consumption is inherently sequential. By sequential, I mean that the second track that I listen to from a playlist has some relation with the first track, and the third track that I listen to from the playlist has some relation with the first and the second track, and so on. Now, some of you Rexis experts, you may immediately map this to a slate recommendation problem. But there is a subtle difference here. Compared to traditional slate recommendation problems, users in the music space, they tend to explore all the items in the playlist. And this is different from, let's say, an e-commerce recommendation or a movie recommendation, where you pick the single best item. So we don't want to recommend the single best track to the user, but we want to generate an optimal sequence of tracks for the user. At this point, when I talk about sequence, some of you would already recognize the crazy permutation combination behind this problem, and this is something that we'll discuss later. So when we talk about the sequence of tracks, this is a sequential decision-making process. And reinforcement learning is a very popular tool to tackle sequential decision-making problems. But with it comes certain complexities. So traditional reinforcement learning relies on the agent having interactions with the real users. And this can be detrimental towards user satisfaction. Let's define the goals of our current problem. So we want to provide an on-demand playlist to the user, which means we want to provide to them the best recommendations based on the current context. And this is in contrast to static playlists, where the tracks are selected and sequenced from beforehand. At the same time, we recognize that it is impossible to select and sequence tracks from the entire catalog of music, because that would probably be infeasible. So, like most standard recommendation systems, we assume that we have a smaller candidate pool of items, and from that candidate pool, we select and sequence tracks. Finally, for user satisfaction, we choose track completions as a proxy. I think this is incorrect, but yeah, we choose track completions as a proxy to measure user satisfaction. So, while all of these goals exist, it is important to remember that we want to train an agent without hurting user satisfaction. So, to avoid exposing an untrained agent to real users, we make use of something called a model-based reinforcement learning. So, the illustration on the left side is a standard schematic representation of reinforcement learning. The top gray box is the environment that emits a state, and the bottom gray box is an agent that consumes the state and produces an action. This action is meant to influence something in the environment towards a favorable outcome. The environment consumes this action and then it responds back with an updated state and a reward based on that specific action. Finally, the agent takes into account the updated state and the reward, and then it adapts its strategy and then generates a new action. And this loop continues. So this is the standard reinforcement learning paradigm. In model-based reinforcement learning, the environment makes use of something called a world model. And this world model estimates how a user would respond to a list of tracks based on the action generated by the agent. So the environment makes use of this world model to consume the action and then generate an updated state and a reward based on that action. The agent in the offline training phase, it makes use of this world model to learn to pick the best selection and the best sequence of tracks in order to maximize the simulated user reward. At this point, it is clear that the world model plays a critical role in the offline training of the agent. We want the world model to be as close as possible to the real users, so that the offline training of the agent can be as close to the real world as possible. The world model is primarily a transitional function, which takes into account the candidate pool of tracks, the user listening history, and the current selection of tracks to respond with an updated state and a reward based on that specific action. Besides these functions, it is also responsible for other functions like starting a listening session in the simulator, maintaining the list of tracks recommended by the agent, and terminating the listening session based on certain criteria. To predict how a user would respond to a track, it makes use of a user model. So the user model is a standard supervised classifier. It is non-sequential in nature, which means it does not rely on the past listening history to generate a prediction for the current track and the current user. It takes into account context features and user features along with track features to generate the prediction. To train this classifier or the user model, we generate data from a random policy. This random policy, we basically shuffle tracks in the random order for a few percentage of listening sessions and show it to the user. And we record their interactions with this random order. And this represents the ground truth data to train the classifier. So using this ground truth data, we basically train the classifier and we have the world model. So the mathematical equation on the left side represents what I'm talking about. The prediction for a given track Y is dependent on the item features for that track T and the user features for the user U. It does not rely on anything else. So we have the user model. Right. At this point, I think we have all the components that we need to build the simulator to train an RL agent. The only missing bit is the RL agent itself. So we want the RL agent to learn an optimal state action mapping pair. By this, I mean, given a state, the agent must learn to generate the best possible action. The illustration on the left side shows a standard RL algorithm called the deep Q network. The deep Q network relies on a deep neural network to estimate something called a Q value. This Q value represents the estimated return of a given track and a user. So it takes into account both the short-term reward and the long-term reward for the user and the track. Okay, before we discuss the limitations of the DQN algorithm, I have to say that the DQN algorithm is absolutely phenomenal. When they published the paper in 2015, some would argue that that is the work that actually brought deep reinforcement learning into popularity. But in our case, the DQN algorithm has certain limitations. It learns representation of a very fixed action space. And in our case, we want the RL agent to learn to cater to a diverse set of user preferences and a diverse set of playlists. So for each playlist, we have a different candidate pool of tracks. And moreover, the candidate pool itself is dynamic and it constantly keeps on changing. So we cannot use a fixed action space for our RL agent. And what is the solution here? Do we just map each track in our catalog to a single action? That's infeasible. Like, we cannot map all the tracks in the entire music catalog to like different actions. To address the scalability issue, we use a modified version of the DeepQ network. We call this the action head Q network. So instead of using a fixed action space, we pass the action representations themselves to the Q network. In our case, we pass basically the track features or the candidate pool of items to the Q network. And the Q network, instead of learning the representation of a fixed action space, it learns to take the representation of the action space from the input along with the observation. And then it learns to predict a single Q value for a given action and state pair or an observation pair. The advantage of this is that it would scale and it would hypothetically generalize for all the playlists because the track information is actually coming from the input. But there is a flip side to it too. It relies on multiple forward passes because it needs to conduct a forward pass for each combination of user and action pair. But this forward pass can be done in parallel. So it is a downside that we can live with because honestly, it doesn't really affect our latency concerns. Right. So at this point, we have the Q value for the user and the track. To construct the playlist, we generate the Q values for all the possible tracks in the candidate pool and the user, and then we pick the track with the highest Q value. After that, we regenerate the Q values for the remaining tracks and an updated state, and then we again pick the highest track and so on. So this way we are able to construct the playlist. Alright, at this point we have the agent and we have the simulator. So we were able to train the agent offline, and the next step is an online test. For the online test, we have a random policy where we randomly shuffle the track. Along with that, we have a second baseline called cosine similarity, which is based on pre-trained user and track embeddings. And finally, as the strongest baseline, we have the user model itself, which is deployed using a greedy model predictive control strategy, or a GMPC, which is like simply we get the score for each user and track, we sort them and present them to the user. So we have 4 baselines. Just a quick note on the target. The user model is a multi-head model, and it has 3 different targets: track completions, skips, and listening duration. And during agent training, during offline agent training, the agent relies on the sum of completed probability given by the user model. So on the left side, you can see the results of our online test. On the vertical axis, you see different policies, and on the horizontal axis, you see the performance for each policy. So the random policy naturally performs the worst, and that is followed by the cosine similarity policy. And you can see there is very little to distinguish between the world model GMPC policy and the RL agent, which is represented by the action head policy. So at this point, we would also like to discuss the offline-online comparison between the policies. So the random policy performs the worst in our offline simulation as well, and this is followed by the user vector policy. And you can see that there is very little to distinguish between the GMPC policy and the RL agent. And this is not really surprising, because in simulation, the GMPC policy is indeed the best policy that the agent can learn. So talking about next steps, one straightforward improvement would be to use more sophisticated user models, because we used a non-sequential standard classifier. So we can go into sequential models and transformers and stuff. At this point, like, we also tried sequential models, but in practice, we found it easier to train RL agents with non-sequential model, because with sequential model, we ran into instability issues and stuff. And the final improvement that I propose here is that once we have an agent trained offline, we can continue training it online. And this is different from supervised learning. Sure, now you have fine tuning and stuff, but like standard supervised network, you don't really retrain it online. But RL agents, it's perfectly acceptable to train it offline and then continue training it online. So with that, yeah, if you like dozed off, I just want you to take 2 takeaways from this presentation. Like, if you're planning to explore reinforcement learning, like simulation-based reinforcement learning is a nice tool to have in your arsenal. And it is fine to just use a standard reinforcement learning algorithm and adapt it to your needs by making simple modifications, and they work. I probably glossed over certain details of this, like of our work, like most of you would have recognized. So we published a paper in KTD this year, and that probably has more details and like a lot better organization of this content. So you can also check that out.
Excellent.
With that, yeah, thanks. I'm at the end of the presentation.
Excellent. Thank you, Surya.